So for this particular aircraft, I started in emergency medical services in Ontario. I've been doing it for 18 years now. This particular aircraft, for me, it was 7 weeks training before I got certified on the aircraft. So how my certification works is the company grants you aircraft certification authority, which means every task that we do on the aircraft is documented, and I have to sign it off. I have a ACA stamp to sign it off saying that I'm certifying that what I did, it's in an airworthy condition, ready to fly. So that's a little bit of my background. So,
are you okay with
sure.
take pictures?
Oh, absolutely, yeah, sure, no problem.
So some of us I couldn't make it. So can I ask to have maybe 4 volunteers, and we'll take turns just taking a video. So we'll do 15-minute videos, and then you'll send them to me, and then we'll have that. Can we do that? Okay. Yeah. Do you want to be number 1?
Yeah.
Okay.
Oui.
Okay, number 2, 3, 4. Okay, perfect. Then we don't have to be all filming at the same time. Okay, great. Thanks a lot.
So I'm gonna just briefly talk about like the construction of the aircraft, and then I'm gonna get right into like the vibration analysts and all that kind of stuff, where I think with our time, which I maybe should be focused on along with other things. I'll take you like through a quick kind of like walk around, describe the aircraft, and then we'll bring everybody up top. They get a chance to have a look around.
And they're just excited to see the helicopter.
Okay, perfect. So, the aircraft's manufactured by Leonardo Helicopters, which is based in Italy. They're an Italian manufacturer, but they also have a manufacturing facility in Philadelphia, which is where we received our aircraft from. So we've had these since 2010. So we've been operating them for a while. They are on maintenance schedule. They're based on hourly requirements. Some items are calendar time. So every 365 days we have to do a certain task. Whatever the maintenance manual of the aircraft says, we follow the maintenance manual. We follow procedures as recommended by the manufacturer of the helicopter. And that's for any aircraft. That's for helicopters, fixed wings as well. So for example, for our aircraft, there's calendar items, but based as it sits here in an operational field, we're doing an inspection in flight hours every 25 hours, 50, 100, 150, 300, 600, 900, 1200, 1400, and it keeps repeating the cycles up to 2400 hours, and then it repeats itself. So for example, every 25 hours, for example, these thermal dampers here, which control the lead leg. So these blades are allowed to lead and lag from this hinge point here. So every 25 hours, we have to inspect this spherical bearing for any kind of wear or like any defects, okay? Terror blades are made out of aluminum honeycomb composite, so they're sandwiched. The leading edge is made of nickel. It's like a nickel abrasion. The tail rotor assembly, what it does is it controls the direction of the helicopter. So the pilots up front, if you get a chance, I'll show you the controls. To control the movement of the helicopter, there's a cyclic, which directs it fore and aft, side to side. A collective, which increases the blades of the main rotor blades to increase pitch, to increase and lower, to lower and raise the helicopter. And there's 2 pedals. They're called tail rotor pedals. And what that does is it controls the pitch of the tail rotor blades for directional control of the helicopter. So under here, what happens is, so this is tail rotor gearbox. There's an intermediate gearbox under that panel there, and a main gearbox. So from the main gearbox, there's 3 drive shafts. There's a section in between the engines, a longer one here, and then it changes direction. And then there's one that goes up here. And in between the drive shaft, there's couplings, which is just fastened together with nuts and bolts. And there's a gear reduction from the main gearbox all the way to the intermediate gearbox, and then it changes direction to the final gearing in the tail rotor. Don't ask me what the numbers is. I don't care right now, really, what they are. So what happens? So the flight controls are controlled by servos. They're called servo, hydraulically controlled. Our systems operate at 3,000 psi, and there's 2 systems on the aircraft. There's a number 1 and a number 2. The number 1 system controls the flight controls only. The number 2 system controls flight control, and we have retractable landing gear as well on the aircraft. So underneath this cup here, at the back of the gearbox, there's a servo with a rod that goes through the gearbox and out to this little scissor assembly. And under that assembly, there's a duplex bearing under there. So as this is rotating, the shaft is stationary, but it's attached to the duplex bearing underneath there. So as that is going, this shaft will slide in and out as well in order to control the pitch of the blades. Okay? Same principle with the main rotor, but I'll get you guys up there for that. The main head assembly is made out of titanium. Again, these are able to have the pitch and to lead and lag. The rotor head, there's different rotor head configurations in the helicopter industry. Some are rigid, semi-rigid, and fully articulated. Our rotor head is fully articulated, which means it can change pitch, it can lead and lag, and it can also flap up and down. Okay, and I'll show you that up there. As far as vibration, vibration is very important to us. We have called a HUM system. It's a helicopter usage monitoring system on it. There's 26 sensors on the aircraft to monitor vibration levels. And we have a guy at our head office in Toronto that monitors. We do a download every 12 hours. We download it from a card to the laptop, and then it gets uploaded to a server where our HUMS guy looks at it. So he's looking for any abnormal vibration tendencies. And he'll say, if we have, let's say if he's picking up a bad reading from a sensor, he'll have us look at the sensor, take it apart, clean it, and then we'll try it again. But as far as for the tail rotor and the main rotor, they're balanced. They are dynamically balanced. If we pull this assembly off and pull it on, we have to fly the aircraft and do a dynamic balance at certain speed regimes. It's like balancing your tire on your car. If you get a new tire on, it's balanced before it's put on to avoid any kind of abnormal vibration. It's the same we have to do for the main rotor and the tail rotor blades. To achieve that, these are called pitch links here, and you'll be able to see them up there a little more clear. These pitch links here, we're able to adjust them to change the pitch of the blades statically, and the blade bolts that hold the blades onto the rotor, onto the tail rotor hub, on the tail rotor hub, they're hollow. So we're able to put weights in there for balancing. And in the helicopter world, there's radial vibration and axial vibration. So the blades for the tail rotor blades and the main rotor blades, they're made of titanium. So they're obviously light but very strong as well. So that's how we achieve the balance. And you can't see it because it's covered under cowl, but there's a sensor here as well, and a sensor under here to pick up any vibrations from the tail rotor assembly. And there's also a sensor on what we call the IGB, the intermediate gearbox down here. So as you can see, from about here to here it's all composite. It's aluminum composite material. So this intermediate gearbox and this tail rotor gearbox, there's a lot of weight hanging off what we call the vertical fin. So it's important. So every inspection, normally we'll do a 50-hour. We'll inspect it here. We'll take all these cowls. These are all cowls. Those will all come off for an inspection. Normally we have heavy maintenance bases as well in London and Ottawa when the machines go down for any major work. So for example, this machine is actually due to go to Ottawa this week for a major inspection where it'll be down for a month worth of inspections and work. Okay. See if I can tell you here. You can see the blades. The blades they can flap. There's elastomeric bearings on the inside here. So elastomeric bearing is a series of laminated rubber and metal plates. So these get inspected every 365 days for any deterioration, but we also inspect it every 3 days. We do a serviceability check. So there's check sheets that we go from one end of the aircraft and around. So we'll grab a flashlight and inspect those every 3 days, or when we're up here doing any other kind of work. Okay? Let's see. Any questions? Tail rotor hub and blade assembly? No? Okay. I'll point out a couple of cool neat things here. So the tail boom assembly here. The tail boom, same thing, it's made of aluminum honeycomb. An inspection of this, for instance, is a 300-hour tap test where we take a little composite hammer, and we tap it to see if we see any debonding from the main skin to the comb, okay? You'll see these are actually an afterthought for this aircraft. These are just reinforcements. So what had happened when these aircraft were first manufacturing, there was a weak point, And then I think it was Dubai, one of the machines, the tail, like they were taxiing on a call, and the actual tail boom folded in on itself and came this way. So they put reinforcement fixtures here and on the other side as well. So the tail boom, so you have the main fuselage and the tail boom. So the tail boom is attached to the main fuselage by 6 bolts. So there's 3 on this side and 3 on the other one. We have to inspect those every 200 hours. So we pop these covers off. One guy is inside of the baggage compartment. I'll show you when we go to the other side. So one guy takes, so there's a bolt and a barrel nut where the barrel nut sits in. So we have to take the barrel nut out, the bolt, inspect the bolt for any defects, the barrel nut, and the structure around it. There's 2 huge aluminum fittings here that the hardware goes through to attach the boom to the fuselage. And it's only 6. And the manufacturer calls to remove the bolts in a specific pattern. So for example, we start on the left side. So everything is referenced as you're looking forward to the aircraft. So this is the left-hand side, or number 1 position, and this is the right-hand side, or number 2 position. So on the other side, we'll go the middle bolt out first, we reinstall that, then the top bolt, then the bottom bolt, we come to this side, then this bolt is taken out. This one, and this one as well. And it's torque to 80 foot-pounds is what the torque is. Just to keep it, yeah, go ahead.
Can you do this here?
Yeah, we do it here, yeah. Yep, we do it here.
How do you hold this? Do you use?
No, the only way we'd hold it, so if we need to remove the tail boom from the fuselage, we have a cradle that we use.
Okay.
But to do each bolt individually, we don't have to do that. The other bolts keep it attached to the fuselage fine. But you can notice a difference when you, I'll get to you in just a second, okay? You can notice a difference when we remove the top bolt on the other side. This seam here is filled in with sealant. It'll open up, it'll go, "Meh." So you can see why that you only do one at a time. Anyway, so yeah, what's your question?
Any sort of lock plate or anything to hold that out?
No, so the barrel nuts are they're pinched, so there's a friction on the barrel nut. So when my partner hands me the barrel nut, I'll take the bolt and thread it in to make sure there's still friction on the bolt. And in aviation, any hardware, if you have the bolt, for that bolt to be in safety, you need about 2 threads exposed past the nut to be safe. It can't be flush with the nut. It's no good. The bolt's too short in that case. Okay?
I got a question.
Yeah, sure.
When you're tightening the
Yeah.
situation, you need to have that torque. Do you use displacement or torque wrench?
Torque wrench.
Combination of both?
Yeah, we use snap-on torque wrench. So the procedure when we put the bolt back in, we put it in, we torque it to 80 foot-pounds, loosen it off. So the initial torque is to set the barrel nut in the groove on the other side of the airframe. Loosen off, then we put the final torque again to 80 foot-pounds. And then what I use, most of us use is like torque seal. So we'll run like a line of like witness mark from the airframe to the bolt. So the next time we come, we can see if the bolt is moved or not. It's all over the aircraft. Okay?
Do some of them have wires going through some of the
No,
fasteners?
no, nothing, no.
But that's sometimes some aircraft have that, do they?
I've never seen it on helicopters before.
For planes.
Maybe.
Yeah.
Yeah, I've never seen it though. I think that's it. Just while I'm here, this is the exhaust nozzle. So this is where the exhaust comes out of the aircraft from the engine. Baggage compartment. Let's go around to the other side. Watch your step and watch your heads around this. I'll just touch on this. So this is a horizontal stab. So what this does when the aircraft's in forward flight, it keeps the tail down. So if you notice, it's a reverse airfoil. It's like an airplane wing, but it's upside down. So for theory of flight, the lift will be created on this side of the horizontal stab, which will push down, and the winglets add for aerodynamic, just like on a commercial airplane as well. And this is attached by 4 bolts to the rear of the fuselage here. So you can see them here, right there, and right there. There's an actual link that comes down from this upper part of the link that attaches it. And we'll come along here on a DI and we'll grab it and we'll see if it has any play. It's one of our checks. And I think it's another 300 hour, we'll do the same. We'll do a tap test to make sure it's not debonded. Okay?
So how many years would you get out of the airframe?
It all depends on, these aircraft, these are These are the, I mean, we've discussed this. These are the most maintenance intensive aircraft I've ever worked on in my career. So we have like specialty areas, like we have A&E, aircraft maintenance engineers that specialize in sheet metal, that just focus on airframe repairs. That's when they go to Ottawa and they go to London. And our sheet metal guys, like, you know, we got to keep on top of these, or they're not going to last us as long as Orange wants them to, you know. So, but like the older helicopters that we had, the 76s, we're averaging now about 7,800 flight hours. We had a 76 in Toronto that had 24,000 flight hours on it. It just kept going. So it's all based on maintenance, you know. Let's see here, baggage compartment for EMS. So all this, to get access to those barrel nuts I was talking about, all this has to come apart and be disassembled to get at it. So there's actual floor here that has to come up to get access. It takes two guys about 6 hours to do the job, just for reference. They're just so maintenance intensive. This is where the crew carries all the gear. In the wintertime, they carry snowshoes in case they have a problem, they have to land in the bush. This is the O2 box. This is what supplies the patients on board with oxygen when we do a call. Okay. Same thing. So as well, these aircraft have pop-out emergency floats. There's 2 on the back and 2 on the front of the aircraft where the bulge is on the front. So they're designed to do, if they have a problem, they have to ditch in water. So they're designed to, the pilots will arm a switch. There's water sensors. There's 4 of them, 2 on the aft under these pylons and 2 on the forward part. So as soon as it touches water, or the pilots can deploy them before they come in contact with the water. But if they don't, for some reason, once the aircraft touches the water and hits the water switches, the floats will deploy. So how they deploy is there's 2 bottles, 4,000 PSI in each bottle. So there's one on this aft and the other one on the aft float. So they're 4,000 PSI filled with helium. And that's what, so the bags would be about this big. So they're designed to keep the aircraft up, afloat in time to get to evacuate the crew. So that's going back to an annual inspection. I'm certified on that. I took the training for that. They're Italian manufactured float assemblies. So that was a week training for me. So that's an example of an annual inspection. So every 365 days, that float has to come off, be disassembled, and it has to be inflated to make sure it holds pressure for a 24-hour period. Okay? So that's an example of an annual inspection. Okay? So like continue on, like I said, it's retractable landing gear off a number 2 hydraulic system. So it's just redundancy but the number 1 system only does flight controls, and the number 2, like I said, does flight controls and landing gear for retraction. Hydraulics, there's hydraulic reservoirs, one on each side of the upper deck. We fill them up. There's like a little pump that we pump them up. We take these caps off and just hook it up to pump it. And we also, if you turn around and have a look at that blue cart over there, we can actually put full hydraulic pressure on the aircraft from a ground cart to check any flight controls or any other maintenance we have to do. Okay. Crew sliding doors. Again, there's emergency pop-out windows. There's a little flap on the inside where the crew would pop it. There's a little rubber strip in there which is designed to pull out, and they push on the corner of the window to evacuate the aircraft. That's another thing that's an annual inspection. Okay. There's a door annual inspection where we have to take the door off, check all the latches, make sure they're all serviceable and in good working condition, and we replace them if they're not. So EMS, and this aircraft is used for like a lot of offshore work as well in the oil fields. Very popular aircraft for that. It was actually designed for that as well, for offshore. So there's lots of aircraft. So this is our stretcher. This is where we carry the patients when we go to do a call. Again, they have all their equipment in there. We're responsible for that as well, for the maintenance of the stretcher and the lifting assembly that lifts it up. We're responsible for all the aircraft, electrical, mechanical, hydraulic, and like I said, we have sheet metal specialists and we have avionics specialists, like electrical specialists. We have a guy here, he's awesome. We love having him. So flight controls. I'll bend down so you guys can see. So flight controls. No, you guys can stand up. I'm just getting. You guys can stand. Oh, so okay, yeah, okay. So flight controls. This is the collective, which increase and decrease the pitch of the main rotor blades to raise and lower the helicopter. This is the cyclic control, which is 4 aft side to side, and the tail rotor pedals as well. Okay. So this aircraft it's IFR equipped. So so we have the same capabilities as a fixed wing aircraft in bad weather going into Toronto. So the pilots can fly on instruments alone. So there's VFR and IFR. So this is a 4-axis autopilot. So the aircraft can basically fly by itself when it's programmed to do so. So just a little bit of that, and these are all just display screens. They just display all the pertinent information that the pilots need to use, like monitoring system, engine parameters, main gearbox parameters, everything. They don't see any vibration. That's just us. That's just from what we download. Go ahead.
How do you plan and document all this inspection?
Okay, so we have a maintenance control system called RAMCO. So that plans and everything. So we'll get a printout. It's alive. So when we come in the morning, we update the aircraft hours, and it's automatically updated right away as soon as we upload. So we know it's called a coming due report. Okay, so we know automatically what's coming due, and then we have maintenance planners in the background that plan. For instance, this. Okay, we're 11 hours. This machine has to be in Ottawa. So it's just like that. But we see it every day. Yeah. Okay.
Can you just
Sure.
things which I think you might find interesting?
Sure.
One is, can you describe why you need to have a certain angle of attack when you're taking off from the top of the hospital, and then also
Okay.
if you have a total engine failure,
Okay.
how it's possible to land?
Okay, sure. Okay, so let's go back around the other way, and I'll take some of you guys up. So I'll just give you like a quick description of what Mark was saying. So this, that, here, I'll show you. Some of you come up. Come on up.
Like, camera.
Stand over here. Stand all around and get
Okay, yeah.
just kind of just leave me a little gap there when I can talk to your fellow classmates there. So this is where the magic happens right here. So the engine is made by Pratt & Whitney of Canada. It's a turbine engine. So the principle of a turbine is it sucks in engine or air, compresses it, ignites it, and then inside of the engine there's wheels, there's discs. Okay. So how it works is it introduces fuel. It's ignited, and the hot gases contact power turbine wheels, and then it goes through a stator. And what the stators do is it directs the hot flow of gases optimally onto the power turbines. So the first stage keeps the compressor turning to suck in air for combustion. The second set keeps this drive shaft turning for the main gearbox. So the whole purpose for the engine is to keep this has to maintain 100% RPM. So it's 302 RPM. So in percentage-wise, it has to maintain 100% PM. All of these they have EEC, so they're all electronically controlled. So with the collective that I showed you, as soon as they lift the collective up to take off, there's 2 units underneath the floorboard called LVDTs, which send an electrical signal to the EECs, the electronic engine controls, to say, hey, I'm increasing power, I need more fuel to the engine to maintain this rotor head at 100% RPM. If it doesn't have 100% RPM, you'll have what they call a rotor droop. So there's not enough speed in the rotor system to maintain flight, so it'll drop, okay? So that's the whole purpose of it. These engines are $1.4 million just for a dollar value, and they're a 5,000 hour overhaul. So they can achieve, once they hit 5,000 hours of operational time, you take it out, send it back to Pratt & Whitney, and they overhaul it for us, and then we get it back. This gearbox is 5,000 hours. The main rotor blades are 5,000 hours, but their time expired. They're destroyed. They're never used again. It's called a life limited item. Okay. So in here, so if they have an engine failure, there's lots of power with this aircraft. They can, if they have an engine failure, if you, whenever you guys see it on the rooftop, when they take off, okay, so they'll take off backwards so they can see the pad. They'll check what we call the P's and T's, the pressures and the temperatures of make sure everything's turning and burning, as we say. But if they do have an engine failure, once they're at that point, they can land. But once they come up and then what we call they rotate over to go into forward flight, if they have an engine failure at that point, they have enough power in one engine to fly away. So the horsepower for each engine continuously is 1,500 horsepower, but they can go what we call OEI, one engine inoperative, to 1,800 horsepower to maintain flight, to get back to base or to land safely somewhere, okay? Inside of here, what happens, inside of this and on the other side too, it's the same. It's called a freewheel unit. So what happens is if an engine fails, so the input into this is 18,000 RPM. All the gear reduction is done in the main gearbox, okay? All these lines that you see here, they're all just external hydraulic lines. All the oil lines to lubricate the main gearbox are internal inside of the gearbox, okay? So what happens is here, there's what they call a freewheel unit or a spread clutch. So when the engine's turning the gearbox and everything's operating as normal, if the engine fails, what happens is that freewheel unit disconnects the drive from the main gearbox. If it doesn't do that, what will happen is if this main gearbox is dragging this engine along, all the weight of the shafting, it's going to drop the rotor RPM, and they don't want that to happen. So what they'll do in case, let's say that if they have a double engine failure, worst case scenario, okay, I'm trying to explain it what happened. So if they're flying along and they have pitch on the blades, what they'll do, they'll drop the collective to maintain rotor RPM because they don't want to lose RPM. They'll pick a landing spot, they'll fly along. Once they come into a flare, it's called an auto rotation in the helicopter. Once they find a spot, they'll pull back in collective to increase the pitch on the blades and to feather the landing. An airplane can't do that, just saying.
But if you lost two engines, then
Yes.
how will you give the thrust?
If you lost two engines,
If
sorry?
you lost two engines
Yep.
in case of emergency, then
Yep.
how will it move forward? There is no thrust.
No, there is thrust. The engine doesn't produce the thrust, okay? The main rotor blades produce the thrust. So so this is a turbo shaft engine. So the thrust is what happens is the airflow in an auto rotation is coming up through the rotor disc. This whole assembly, when it's turning, is called the disc. In an auto rotation, it's the opposite. Air is coming down in it. So the main rotor blades and the direction when the pilot goes forward. So what happens is the swash plate, if they're flying along, this whole disc swash plate assembly is tilted forward. So when that happens, so with the rotor disc, there are advancing blades and retreating blades. So when the blade comes around at the forward part of the helicopter, the blades are at a lower angle of attack. When they come around up the slope that the swash plate is creating, they're at a higher angle of attack, which increases the lift on the back part of the helicopter, moving it forward. So as long as they keep that forward momentum in the blades, they can have a dual engine failure all day. They'll still be able to land the aircraft. I hope that answers your question. Okay. So yeah, like I said, so this is the only aircraft that I've ever seen worked on that direct engine output into a gearbox is directly into the gearbox. Most helicopters that I've worked on has the output from the engine. There's a reduction gearbox, then another shaft to go into the gearbox. This is straight 18,000 RPM into the gearbox, and all the reduction is here. So it goes from 18,000 RPM here to 302 RPM at the rotor head. Okay? Sorry? It's a planetary gearbox. Yeah, there's sun gears, planetary gears. Yeah, exactly. The engine has 5 main bearings. There's 3 rollers and 2 needle bearings, I believe. I can't remember off the top of my head. But this is a fuel control unit. Like I said, everything is done automatically. All the pilots do is rotate a switch, and all they do is monitor all the parameters. They monitor oil pressure and temperature. They can start up to 800 degrees Celsius. Continuous operation is about around 500 degrees Celsius. That's the temperature. And there's internal probes that go inside that give the pilot the indication as well of what the temperature of the engines are. What else can I do? It's oil. They're oil. They're turbine oil lubricated. Same with the main gearbox. It's all turbine oil. Yeah. Sorry. Yeah, it's all pure synthetic. Yeah, exactly. It is. Yeah, yeah. So the main gearbox has two pumps, one on the left side, one on the right side. If there's any problems with either gearbox or the engine, we have what we call chip detectors. So there's two main lower sump detectors and one mass detector up here. So if they fly along and they get an indication, they'll get a main gearbox chip light, for instance. So they have the ability to burn that chip. If it's just fuzz, if it's insignificant, they can burn it up to 3 times. If it latches a 4th time, they have to land as soon as practical. So that's when we come in, we pull the chip detector out, analyze the size of the flakes, and then we'll send those flakes to a company, I think they're in New Jersey, to analyze what the material of the chips are. Whether it's part of the gearbox, gear teeth, bearing material, they'll analyze it for it, get back to us. They'll talk to my chief engineer, Leonardo, and make a decision of where we go if we're changing the main gearbox, for example. It's filtered as well. There's a cooler on top as well to keep all the temperatures within parameters. Sometimes in the summertime, they'll get really warm, so we'll have to remove the cooler because sometimes. So this is actually sucking air down to the cooler. There's a fan under here, so it actually pulls the air through. It's like the radiator on your car, so it pulls air through. So with that pulling through, instead of blowing up like some blowers do, you're going to accumulate all the where we land, all the sand, all the dirt, you know what I mean? So it gets quite dirty sometimes. And if they run into temperature problems with the main gearbox, we pull it off and back flush it and clean it and reinstall it. Yeah.
I have a question.
Sure.
What are the main causes, the main modes of failure that you have here?
Geez, it varies. Like it varies. It really does. There's no like for our aircraft, I would say a problematic area are the main gearboxes for our aircraft. No, making metal. So this is an accessory gearbox made for only us. So the object was to start one engine without the blades turning, and then start the other one, and then engage the rotor head. But we don't do that. So this accessory gearbox is not on any other AW139 in the world. This was just for us. This part of the main gearbox is causing issues for us. It's making metal, causing us to change the gearboxes. Yeah. So if you'll see, so same as the tail rotor, there's main rotor dampers up here. So you can see, so they're hydraulic filled. The other ones are elastomeric bearings, okay? Maintenance wise, they're, what are they? 2,400 hours overhaul, but we change the hydraulic fluid every 600 hours for maintenance purposes, okay? And as you can see, there's elastomeric bearings here as well. And these are the flap stops. So like I said, this is a fully articulated head. It can come up, it can flap, it can change pitch, and it can lead and lag. And I'll show you if you just want to step that way. I'll show you. Show you what I mean. So it's free to do that in flight. Oh, the only thing that's controlling that movement is the damper, is the cushion of the damper. So these things are like wet noodles flying around, basically. They're able to do where they're able to position what they want. So for track and balance purposes, these pitch links here, right here, we're able to adjust the length of those. So to put it in track, between all 5 blades, we're allowed to be 10 millimeters within track of one another, okay? So all that's picked up by the hum system I was telling you about. But these pitch lengths, let's say if we have one blade that's flying away on us, so we'll take it, let's say it's flying too high, we'll take that pitch length and we'll loosen these jam nuts. It's like a turnbuckle, and we'll shorten it to bring it within. And it literally takes like an 1/8 of a movement to make a big adjustment. Same thing, the main rotor blade bolts, they're hollow, and we put weights in there for balance as well. Yeah, go ahead. So it all depends. So the most, I think, I gotta remember the book. I think we're allowed up to 800 grands in one blade. I think, don't quote me on that, but I think that's where we're allowed. But sometimes, if we look at the pattern of the hums, sometimes what we'll do, instead of adding weight to one location, we'll remove weight in the opposite location to balance it out, right? So the swash plate, so this is mounted on a ball basically, and this can rotate at 360. So it's called, what it does is it transfers rotary motion into push-pull motion. So how this rotates is this rotor head sits on a mast that comes up. The rotor head is, it sits on a set of cones. So there's a cone on the bottom and a cone on the top. And on the top, underneath this hat, there's 12 bolts. So there's 12 bolts, max torque to 56 foot-pounds, that squeeze the rotor head to keep it onto the mast. So when we do the initial check, we have 5 attempts to make, so we have to do a retorque check once we reinstall it. So every 10 hours of flight, we have to check it. We're allowed to check it up to 5 times to make sure it passes torque and that it's holding torque. And then it's safety with lock wire. There's 12 bolts, okay? So how this is driven, so so this fits on a spline shaft. As the gearbox is turning and the rotor head is turning, this scissor assembly is connected via this link here. So this is called a scissor assembly. That's how the swash plate moves as well and is able to do that. So what would happen is if there was a problem, if you lost this, then you'd lose partial flight control if anything happened to that. Okay, but that's how it maintains and rotates with the rotor head. So as that's moving, there's three main rotor servos, hydraulically actuated by 3,000 psi. That there's one in the forward, one on the right-hand side, one on the left-hand side. And as the pilot's moving the stick, those servos do different things. And for a helicopter, they're positioned where any input, the act is actually 90 degrees in direction of rotation. So it's called gyroscopic precession, okay? So anyway, so if you were to see this, and I think I have a video. I have a video of it. I sent to a buddy of mine. I'm gonna send you the video, okay? Of because we had hydraulics on one day, and I sent a video of this like moving around. So that's what controls basically the pitch of all the blades and how it can change. So as well, so if the aircraft wanted to move to the right, say, so that swash plate assembly would tilt to the right. So again, so in the direction of rotation, there'd be less angle of attack on the blades coming to the left side of the disc. As the disc made its way around, there'd be more pitch. There'd be more pitch on this side of the blade than this side of the disc, causing the helicopter to go right. So it's literally based on the angle of attack and the disc rotation. Yeah. And how we get the blades done as well. See, if you look at the tip of that blade, there's like there's a little tab on the end of that blade there. If you look inboard a little bit, come my way, there's a little tab. See this right here? Right there? So there's one on the outboard portion of the blade. So we can use those, they're called trim tab adjustments, to adjust how the blade flies as well. So if we bring that little tip down, it'll adjust the blade, it'll bring it down. If we push it up, it'll allow the blade to come up as well. Yeah, basically, exactly. Exactly.
But is this controllable here, or do you need to bring here to?
Yeah, we need to make all of these adjustments. It needs to be here. Yeah, yeah, exactly. We need to do all the adjustments are manually done. Yeah. So once we do the adjustments, we take it back out, we fly it. So there's regimes. What we'll do at 100% flight idle ground. We'll check it if it's within limits. So what we try to achieve is below 2.2 IPS, inches per second of vibration. So we'll check it at 100% when it's at 100% rotation. If it clears there, then we'll take it into a hover at 80 feet out of ground effect hover. Then we'll do 80 knots, 100 knots, and 140 knots, and then VNE. And VNE is velocity not to be exceeded, which is about 155. So all those 5 regimes will check all the balance marks for it. So if any one of those are out, the computer program will tell us what adjustments to make. Yeah. Here's an example of, so there's a sensor, a hum sensor for vibration. So, like I said, on the aircraft, there's 26 of those sensors picking up all the vibration over the aircraft. The only place it doesn't is on the engines. Pratt & Whitney wouldn't allow Augusta, the helicopter manufacturer, to put accelerometers on their engines for some reason. So,
One more question.
Yeah, sure.
Do you need to do any adjustment because of really, really cold weather?
no, we don't.
Okay.
No, we don't. Not usually. But we will have problems in cold weather. Like these dampers, they like to leak. The shocks, like the shocks in your car that are on the main landing gear and the nose landing gear, they like to leak in cold weather because everything compresses and contracts and they seal. Yeah, these really like to leak in cold weather. Yeah, they do. For instance, I'll give you an example of maintenance and how extensive it can be sometimes. So, a few years ago, these main rotor damper assemblies. There's an EMS operator out west called Stars. So they operated these aircraft at one time. So Stars actually had one of these dampers fail in flight. So the body of this spherical bearing cracked, failed, and came out in flight and hit the rotor blade. So the crew landed to inspect it. So after all that was said and done, there was an emergency AD, airworthiness directive, put out. Every 3 hours of flight, we had to check in this area for cracks and to sign it off to say there was no cracks in it. So what that meant for me, that happened on the July long weekend. Because we fly out more in the summertime, it's the shock trauma season. I was here every 3 hours to do that inspection. There was 3 of us. So I was on call. There was a guy for morning, afternoon, and then I would do night if we ran into that situation. So that's how just serious. So they bring out an AD and we come in and we inspect it to make sure it's okay to clear the aircraft for a safe flight. Yeah. It's just a visual inspection. That's it. Yeah. Just a visual. But all of these have since been like upgraded to the latest and greatest. Augusta came out with sort of like a revamp. Yeah, they had to. They had no choice. Yeah. Go ahead. We do not, but we send parts out. See this part here? This scissor link assembly? Can you see that? That actually goes out for NDT when we replace. So inside of that, how it's assembled, the 2 pieces mate together and there's bushings in there. So before we replace the bushing, that link has to go out for NDT for the ends where the bushings go in. Yeah. What else can I tell you?
Can we maybe cycle some people up?
Yeah, oh, absolutely. Yeah, sure. Okay, you guys, get out of here. Yeah, that's the hydraulic actuator. That's called a servo. Yeah. Sorry? It is not connected to that. So up here, it's called, so this here, this does not rotate. That's called a stationary swash plate. This is a rotation swash plate. It's hydraulic, yes. Yes. In the case of leakage of the servos, we replace them. So we have certain limitations. For example, we're allowed 1 cubic centimeter per 1 hour. So if we determine it's over that, we'll put the hydraulic card on and we'll operate it to make sure it's within limits or without limits. If it's out of limits, we'll change it. Yep. How do we check it? Oh yeah, so if it's leaking beyond limits, we pull it off and send it back to the manufacturer for repair.
Is there any limit or scheduling of that number?
There is not, no. Yeah, absolutely, go ahead, take a picture if you want. Yeah, sure.
One question.
Sure, go
is,
ahead.
Why the end of the blades are different direction? 3 up, 2 down.
Oh, you mean the trim tabs?
Yeah.
Oh, okay.
And off.
At the end of the blades, so
Yes.
I think I know what you mean because that
Different direction.
so that can all be so wire this down and that's up.
Yes.
So watch, I'll show you. Okay. So this whole assembly can tilt. See this? This is called a droop stop ring right here. So watch, I'll show you. Let me show you something. Watch yourself. So watch that side. Okay.
Okay.
See that?
Yeah.
I can lift it up. So that's why. So that ring that ring is able to slide, which will change the position of the rotor
Yeah.
blades, how it's sitting on it. Is that what you mean?
Yes.
Yeah.
Okay.
But at the tip?
The trim tab?
Yes.
Yeah. They can,
Up.
Yeah, they can be up. It all depends on to get the track. We can change them around.
Just up or down.
Yes, we can.
Oh.
Yes, yes, yeah. We can
Thank you,
adjust.
thank you,
Yeah,
thank
we can adjust up or
Yeah,
down.
yeah.
And there's certain amount of degrees we can only go up or down. I think it's 5 degrees. Yeah.
That's why I
We
saw.
we have a tool we can put on the blade with a bending tool that measures how much we're bending it
Oh.
to make sure we're not going past the limitation. Yeah.
Thank you.
You're welcome. Anytime.
啊，我还以为是固定的，为什么3个朝上2个朝